afternoon, everyone. Hello. So I'm very happy to introduce to you Professor David Meier of the Caltech. Our joint program speaker today. Professor David Meier received his PhD from the University of Texas at Austin in 1977, working with the 3 different advisors on the broad research topics. These topics were firstly, developing the theory of MHD jets in the collapsing supernova cores. This is together with Professor Shuran. And second project, thesis project, was predicting the appearance of the proto-galaxies. Now these are known as the Raven-Break galaxies. It was very pioneering work. This is done with Professor Tinsley. His third project, thesis project, was to developing a theory and also predicting the appearance of the radiation-driven winds from the super Eddington accretion disks around black holes. So this project was together with Professor Wheeler. After getting PhD, he continued this line of research as a postdoc fellow at Caltech in the Professor Kipthorne's group, and then at the University of Cambridge in Professor Martin Lee's group. So in 1980, so he became faculty at the Caltech's Jet Propulsion Laboratory, JPL, and where he also began to work in the observing and engineering projects, including the interferometric experiments, such as VLBI, piece of missions, as well as also the theoretical development of the Tareq algorithm for the astrophysical computations. He was also the head of the Galaxy Evolution Group at JPL. And in collaboration with the Caltech colleagues, so Professor Meier performed some of the very first pioneering simulations of the magnetized jets relevant to its talk and in 1980s. And he has continued this work with the Dr. Nakamura, Masanori Nakamura, is our colleague here at ASIAA. So Professor Meier currently is retired from JPL, but he continues his research at Caltech. So he's working on the theoretical interpretations, the radio, the high-resolution VLBI observations of the jets from the black holes. So today, so Professor Meier will tell us about the black holes, the ultimate engines. Let's welcome Professor Meier.
Thank you. Can you hear me with the microphone? Is that all right? Okay, good. I am really happy to be here. I have received wonderful hospitality from ASIAA and the university. I actually was here for the meeting last week on M87, and I'm continuing to be here to talk to you and then to work with Dr. Nakamura the rest of this week. The title of the talk is Black Holes, the Ultimate Engines, and the reason that I use this title is that what I'm going to do is kind of give an overview of my book. And my book is called Black Hole Astrophysics, the Engine Paradigm. I wanted it to be the ultimate engines, but Stringer Verloc said it didn't sound sophisticated enough. So we wanted Black Hole Astrophysics, the Engine Paradigm. So that's what it is. The book is kind of big with lots of equations, but some of it is fairly light reading. That's our newest grandchild, and I think I know how she got a hold of the book. It was my wife who sent it in front of her for that. But I'll only show a few equations today to mostly give you information and processes as to what's going on in black hole systems. If any of you attended Professor Ramesh Narayan's talk on Monday, you will see some of the same things, but Professor Narayan focused on numerical simulations, and he talked about a lot of analytic work that had been done prior to that. I will concentrate on the analytic work and show just how much we've been able to understand even before simulations were brought on the scene. So here's the outline. For those who don't know much about black holes at all, there will be a section where I will give some information that maybe some of you already know, and my apologies for that. What are the different types of black holes? What is it? How big can they get? How do they form? And what's the difference between formation, black hole formation, black hole growth, and black hole fueling? A lot of times these words are used interchangeably, and the three of them are quite different. Then I'll talk about black hole engines. This, after all, is a talk about engines, and I'll describe why we call it an engine. This actually was used long before we knew what we know now. Way back in the late 60s, in the early 70s, they called it the central engine, which was lighting up all of the gas clouds in a quasar. But they had no idea that it really was very much like an engine, an internal combustion engine. How is it? Are they exhaust systems? Yes. How is the engine fueled? How is it throttled so that you can have a low or a high rate of fuel consumption? And finally, because I will have given you so many different kinds of astrophysical black holes in the beginning, I'll show how they can be classified in some regard by the amount of mass that the black hole has and the rate at which it's being fueled. And there's also some belief, but this has not all been worked out yet, that the black hole spin actually also is important in the production of jets. You've heard about black holes being introduced into particle physics, membranes and heat grains and all of those things. Black holes are very much like a particle, especially at the microscopic level. They have mass, they have spin, and they actually can have a charge, and they probably also can have other quantum numbers like color. What we deal with astrophysically, though, is primarily just mass and spin, because astrophysical black holes that are fairly large, they will discharge themselves very quickly because of the astrophysical environment. They can hold a charge for a while, but if you get material coming close to it, it will actually be ejected. I don't think we'll get to this, but if we do, I'll tell you a summary of what we know and what we still don't know. So, first I'll talk about the many, many different kinds of black hole systems. And I'll start with the lower mass black holes, which are, we call stellar black holes, stellar mass black holes. They sort of range from 3 solar masses to 300. And we'll talk more about mass categories in a little while. So the first example are the X-ray binary black holes. There are high mass black holes, which mean not that the black hole has a high mass, but the companion star, in this case, in Cygnus X1, it's a 20 solar mass supergiant star, blue supergiant, that's losing mass toward the black hole, and that's producing X-rays. And then there are low mass ones, which I'll show you a picture of in a minute, which have a low mass star compared to this supergiant. There are ultraluminous X-ray sources. They're actually much more luminous than sources like these. Very close to what we call the Eddington limit. We will talk about the Eddington limit a little bit. And And this produces fairly hard X-rays, fairly high energy X-rays, whereas the ultroluminous sources produce softer X-rays. And here you can see a picture of the two antenna galaxies colliding. Here it sort of looks like an ant in a way with the two different antennae. And here are the two galaxies colliding, and they have caused a lot of star formation. And inside the star-forming clouds are these X-ray sources that are being viewed here by a Chandra X-ray image. And then there's a special kind of X-ray binary called microquasars that there are something like 50 now known or more. The first one was the Granat source 1915 plus 105, discovered by Felix Mirabel and Luis Rodriguez back in 1992. That is also a roughly 15 kilomass black hole, also with an accretion disk, also pulling matter off the star, but the star is low mass, so this is a low mass X-ray binary. In addition, it produces a jet, which is what gave it the name microquasar. If you compare its luminosity with regular quasars, it's more like a billionth rather than a millionth, and so perhaps they should be called nanoquasars. Microquasar is the name that has stuck. And finally, something you may have heard of recently are the merging black holes that were discovered, they were discovered last year but reported this year. And let me start this little simulation for you. You can see the two black holes orbiting each other, and they turn into one. There, and it stopped, and here's the single black hole that they formed. It is not quite the sum of the two masses. It's a little bit less. And the reason it's not, as you probably know, is because this produced a lot of gravitational waves that were strong enough to reach Earth, even though this is about a fair fraction of a gigaparsec away. I think they reported as 1.2, 1.3 billion light years, which is about a 40% of a gigaparsec. So those are stellar mass black holes. These things are about 30 times the mass of the sun when they collided. The next level is sort of the intermediate mass black hole range from 300, which is where we ended off before, to about 30,000. These are very elusive. Over the last 20 years or more, people have found examples, and then within a year or two, someone comes and says, no, that's not right. The data were misinterpreted, or the noise is too great. And, but here are a couple that have so far stuck around. The biggest one is HLX1 in a galaxy named ESO 243 minus 49. Its original estimate was greater than 500 times the mass of the sun, and more recently it's been pegged at something like 10,000 solar masses, which is very close to the, so it was close to this limit, close to being called something other than intermediate, but it's a really good candidate for it. There are other ULX sources, ultroluminous X-ray sources, that appear to be very, very bright, and yet not accreting a huge amount of material that would make them produce a wind, a radiation-driven wind. And when you analyze them, you find that the reason they're so bright is because they have so much mass, and they can accrete new mass at a high rate and still look like a regular old X-ray source at a very high luminosity. And one is the brightest X-ray source in Messier 82. Here's that galaxy here. It's an extremely active galaxy with a huge explosion. Here's the galaxy, and this is the huge explosion above and below. And the 400 larger solar mass black hole, M82X1 is actually this. This is an inset, a Chandra inset from right here. And so this black hole is actually somewhere here near the center of the galaxy. And similarly, there's a brightest X-ray source in NGC 1313. And here it is in the optical, and here it is in X-ray. And I can't even see it on here, but there is a sort of a set of circular rings here, which is where the X-ray source is located, something right here. And if you compare this arm of the galaxy to this one, the X-ray source is somewhere in here. Its optical brightness is very low, but its X-ray brightness is huge. It's a roughly 5,000 solar mass black hole, and but the optical luminosity is low. So it's, in some sense, it's a source that is in a low luminosity state, but it has a big black hole, so it's rather bright. Now finally, this was the first type of system that was discovered, and we just had a meeting last week on this galaxy right here, Messier number 87 in Charles Messier's catalog. Heber Curtis, back in 1918, took a short exposure of the galaxy and found that, yes, you can see the core of the galaxy, but you can also see there was a strange stick or a line of light, and he had no idea what that was. He knew it was made of material, plasma, but he didn't know what it was. And so the last 100 years have been spent trying to figure out what's going on. This is obviously a jet that's being ejected from a very large black hole in the center. And last week's meeting was all about the properties of this galaxy system, the black hole that's in there, how do you produce this jet, what are the different parts of the jet, and how does it accelerate its plasma. It's a very interesting object, and it becomes a Rosetta Stone for many other galaxies that are further away that we can't analyze as well as we can analyze this one. This one is only about 16 megaparsecs, or what is that? Roughly 50-something odd million light years away. Later on, in sort of the mid-century, Carl Siegert discovered secret galaxies. This is a secret galaxy. It's quite different from this one. This one is a spheroidal galaxy, sort of like a ball of stars, whereas this one is actually a flat disk, and we're looking at it face on. And in the center of the disk is at the center of the galaxy is a very bright object, which is producing a lot of light. The gas is moving very quickly, sometimes well over 5,000 kilometers per second. And that is a prototype, or that is a typical example of a secret galaxy. Obviously, there must be some sort of black hole in the center, and that's what has been determined. About mid-century of last century, radio galaxies were discovered. These were radio sources. Here's a very nice looking one that were identified with a galaxy, something like this. And the galaxies were largely spheroidal. The galaxy's down in here, and then there are jets coming out with very strong radio emission. Now, to give you an idea, this from end to end, this must be probably 100 or 200 kiloparsecs, meaning maybe 300 to 600,000 light years across. It's a very large object. And the galaxy is small in comparison to the radio emission. I might point out that in M87, when the radio telescopes got more powerful, it was found out that M87 has an enormous set of lobes. They don't quite look like this, but they are an extremely large set of lobes that have been filling and radiating for many, many millions of years. So M87 is a radio galaxy in the same vein as 3C272.1. In fact, they're in the same cluster, right? M87 and M84. And then Martin Schmidt discovered things called quasars. They were discovered primarily from their spectra that have been redshifted over a very large distance by those standards in those days. And that indicated that they were receding. 3C273 in particular was the one he discovered, was receding at about 16% the speed of light. That was unheard of in the early 60s, back when I was in grade school. This is 3C47. It's a much more beautiful example because you can compare it to the radio galaxy 3C272.3, and you see quite a difference. In this galaxy, the bright emission is sort of near the where the galaxy is, the bright radio emission, whereas in 3C47, bright emission is way out here at the end of big lobes. You can see a jet coming out here just like you can here, and there is a galaxy down here as well. The reason is that this jet is moving transsonically or subsonically, and it just kind of falls apart. This jet is moving supersonically, and it plows all the way out to the lobes and produces nice, bright hot spots. The reason these were the first evidence of black holes is that you add up the energy in these lobes, and you get something that's of order 1 million or 10 million solar masses that had to be annihilated entirely in order to produce the energy, including the emission, the magnetic fields, the particles that are in those lobes. So there had to be millions of solar masses of material annihilated right down here, and the only mechanism people could think of is, in fact, black hole accretion. Then the discovery of radio quiet quasars. They look very much like these, but in fact, no radio, just very bright star-like things. By the way, quasar stands for quasi-stellar radio source. And that fits very well for the radio ones, but for some reason the name was kept for the radio quiet ones. So these are quasi-stellar radio quiet radio sources. And a similar kind of object, the Biela Lacertae. Biela Lacertae was thought to be a star back in the last century, and in fact, it looked like a variable star. But when it was analyzed in detail, what it really is a jet pointing right at the Earth within 6 degrees of the line of sight. And those are called, now we call them, the whole class, blazars, after the first one, Biela. It wasn't until the 70s and 80s that luminous infrared galaxies were discovered, known as LIRGs. They were discovered primarily with satellites like IRAS, the infrared astronomy satellite at JPL, and then more powerful ones like Spitzer, and then WISE. The LIRGs are galaxies that are very bright in the infrared, above sort of 100 million solar luminosities. Sorry, 100 billion, 10 to the 11. ULIRGs are ultra-luminous hyperluminous infrared galaxies are above 10 to the 13. They now have found a few that are above 10 to the 14. 100 trillion solar luminosities. And initially they thought, well, it was a lot of star formation enshrouded by dust. No, it turns out, well, some are, but some turn out to be black hole systems embedded in dust in the center of a galaxy that's undergoing a lot of star formation. Okay, and finally, we'll go to the other end. Oh, I'm sorry, sub-millimeter galaxies, similar thing, except they're at very high redshift, so they've been, they're very distant, they've been shifted from the infrared into the sub-millimeter. And now on the other end of the spectrum are the very, very quiet galaxies. They don't produce much radio, they don't produce much optical or infrared. They are largely inactive. And our galaxy is one of them. What you see here is an infrared image of the center of our galaxy. And these infrared emission points are not the black hole. These are stars, large giant stars. And they're orbiting the dark mass that's in the middle here. And one that's very interesting is this one that has a very elliptical orbit. And here is it's going around this and this point here, and the same thing is true of all the other ones. They're orbiting a mass that you can calculate, and it's 4 million times the mass of the sun. It turns out to be a fairly puny black hole as the cosmological scheme goes. Now, how do you make sense of all these things? Well, what they first started to do in the 70s and 80s was to try to unify by brightness contrast. I mean, a Seyfert galaxy has a very bright optical thing with a galaxy around it, and quasars have a very bright optical thing, and some seem to have a little fuzz around them, but we couldn't quite figure out what the fuzz was. But in the 90s, in the 1990s, when they used